All right, let's go.
Number 1. The source. A single bottle of hydrogen gas. Here's what nobody tells you about the most powerful machine ever built by human hands. It starts with a tank of hydrogen gas the size of a fire extinguisher. That's it. That's the origin of the beams that will eventually collide at 13.6 trillion electron volts, the highest energy ever achieved in a laboratory in the history of physics. The whole thing begins with hydrogen, ordinary hydrogen, the first thing that formed after the Big Bang, the fuel of stars. CERN's engineers strip the electrons off hydrogen atoms using a strong electric field. What's left are bare protons, single particles, each one carrying a positive charge and absolutely nothing else. But here's the first mind-bending fact. The proton beam that eventually tears through the LHC at 99.9999991% of the speed of light contains roughly 300 trillion protons per beam. And all of those protons, every single one, came from that bottle. The amount of hydrogen consumed to fill the entire LHC with beam and run it for hours? Less than a millionth of a gram. Less than the mass of a single grain of sand. The energy comes from the machine. The matter barely matters at all. Number 2. The first accelerator. Linac 4. The protons don't go directly into the LHC. They can't. They need to be pre-accelerated through a chain of 4 increasingly powerful machines before the LHC ever sees them. Think of it like a runway, a very long, very strange runway. The first machine in the chain is Linac 4, a linear accelerator 86 meters long. It doesn't accelerate protons, it actually starts with negatively charged hydrogen ions, hydrogen atoms with an extra electron attached. Those ions get fired down the tunnel and accelerated by oscillating electromagnetic fields to 160 million electron volts, roughly a third of the speed of light. At the end of Linac 4, the ions pass through a thin foil, a stripping foil, that tears away both electrons and leaves only bare protons, clean, ready. The stripping technique is deliberate. It's called charge exchange injection. It lets engineers fill the next ring with far more particles per cycle than older methods allowed. More particles means more potential collisions later. Every step in the chain is optimized for one thing: density. The denser the beam, the more likely the protons are to actually hit each other when the time comes. Number 3. The booster and the synchrotrons. The machine getting ready for the machine. From Linac 4, the protons enter the proton synchrotron booster, 4 stacked circular rings, each 25 meters in radius. The protons are pushed from 160 million electron volts up to 2 billion electron volts. That takes seconds. Then they go to the proton synchrotron, the PS, a machine built in 1959 that is still running today, still part of the chain feeding the most powerful accelerator on Earth. The PS takes the protons from 2 GeV all the way up to 26 GeV. Around this point, the protons are already moving at 99.9% of the speed of light. Then the superproton synchrotron, the SPS, 7 kilometers in circumference. It ran its first beam in 1976. In 1983, it discovered the W and Z bosons, the particles that carry the weak nuclear force, and earned its operators a Nobel Prize. Now, its main job is handoff. It takes the protons from 26 GeV all the way up to 450 GeV before injecting them into the LHC. 4 accelerators, 4 handoffs, each one boosting the protons to a speed the previous machine couldn't reach. The chain took decades to build and is still in operation every single time CERN runs a physics experiment. Number 4. The ring. 27 kilometers of the coldest place in the solar system. The LHC sits in a tunnel 100 meters underground, straddling the border between Switzerland and France. The tunnel wasn't built for the LHC. It was originally dug in the 1980s for a previous machine. The LHC simply took it over in the 2000s and filled it with something far more extreme. The ring is 27.7 kilometers in circumference. To run it, you need the protons to travel in a circle. Charged particles traveling in a circle want to fly off in a straight line. That's just physics. To keep them curving, you need magnetic force. And to get the magnetic force strong enough to bend protons moving at near light speed, you need a magnetic field of 8.33 Tesla. That's 200,000 times stronger than Earth's magnetic field. You cannot generate that with ordinary copper electromagnets at room temperature. The resistance would require so much electrical power that it would be economically and practically impossible. The LHC's 27-kilometer version would have to be 120 kilometers long to reach the same energy using normal magnets. So, CERN built the magnets from niobium titanium wire, superconducting wire, cooled to 1.9 Kelvin, minus 271 degrees Celsius, colder than the average temperature of outer space, which sits around 2.7 Kelvin. The LHC is the largest refrigerated system on Earth. It uses superfluid liquid helium to maintain that temperature across the entire tunnel. At 1.9 Kelvin, the niobium titanium loses all electrical resistance. The current flows forever without loss. The magnets carry up to 11,850 amps and never heat up. There are 1,232 of these dipole magnets, each 15 meters long and weighing 35 tons. They occupy 18 of the 27 kilometers of tunnel, plus 392 quadrupole magnets to keep the beam focused, plus thousands of smaller correction magnets, over 9,300 magnets total, all superconducting, all cooled to near absolute zero, all working in precise coordination to keep two beams of protons traveling in opposite directions inside a pipe the width of your fist. Number 5. The acceleration, radio waves, and a 20-minute sprint. Once inside the LHC, the protons are still only at 450 GeV. They need to reach 6.8 TeV, 6.8 TeV per beam. The machine that does this is not another magnet, it's a radio frequency cavity. There are 8 RF cavities per beam, 16 total, positioned around the ring. Each one oscillates at 400 megahertz, 400 million cycles per second, delivering 2 megavolts of accelerating force each time a proton passes through. The protons don't pass through once. They circle the ring 11,245 times per second and get a small kick from the cavities every single lap. The ramp from 450 GeV to 6.8 TeV takes roughly 20 minutes. The protons are circling at nearly the speed of light the entire time, getting nudged slightly faster with each pass, the magnets ramping up their field strength in sync to keep the beam on course. When they reach 6.8 TeV, both beams have a combined energy of roughly 700 megajoules. That's the kinetic energy of about 900 cars traveling at 100 kilometers per hour, stored in a beam of particles thinner than a human hair. At full energy, the proton beams are squeezed down to a width of about 20 micrometers at the collision points, a fifth of the diameter of a human hair. That squeezing is done by the quadrupole magnets, a final focusing step that dramatically increases the probability that protons from one beam will actually hit protons from the other. Each beam contains up to 2,808 bunches of protons. Each bunch holds around 100 billion protons. They pass through each other at the collision point 40 million times per second. Number 6. The collision. What actually happens when protons meet? Here is where people get confused. When the beams cross, the protons don't collide like billiard balls. They collide like tiny, fuzzy bags of even smaller particles. Protons are made of quarks and gluons, a seething internal structure held together by the strong nuclear force. When two protons collide at 13.6 trillion electron volts, it's actually the quarks and gluons inside them hitting each other. That collision converts kinetic energy into mass. Pure energy becomes matter. E equals mc squared running in the production direction. Energy transforming directly into matter that didn't exist a microsecond before. The debris from each collision sprays outward in every direction. New particles. Particles that don't exist in ordinary matter. particles that existed in the universe for fractions of a second after the Big Bang and then vanished, never to form again under natural conditions, until CERN recreates those conditions deliberately, on demand, 1 billion times per second. The Higgs boson was found this way in 2012. It lives for less than a billionth of a billionth of a billionth of a second before decaying into other particles. CERN never sees the Higgs directly. They see its decay products and work backward to prove it was there. That's what this machine is actually doing, not watching particles, reconstructing the ghosts of particles that died before any detector could touch them. Number 7. The detectors. Cathedrals for particles. The LHC has 4 main collision points, 4 massive detectors buried underground, each one wrapped around a spot where the 2 beams intersect. Atlas is the largest, 46 meters long, 25 meters high, 7,000 tons. It's built in concentric layers like an enormous onion, each layer designed to catch a different type of particle. When a collision happens inside Atlas, the debris flies outward, and each layer captures a different piece of information: energy, momentum, charge, trajectory. CMS, compact muon solenoid, weighs 14,000 tons despite being physically smaller than Atlas. It contains a superconducting solenoid magnet generating a field of 4 Tesla. Its iron yolk alone weighs more than the Eiffel Tower. Alice studies quark-gluon plasma, the state of matter that existed in the first microseconds after the Big Bang, before quarks and gluons cooled enough to form protons and neutrons. It recreates that state by colliding lead ions instead of protons. In 2025, the Alice team used new oxygen-oxygen and neon-neon collisions to capture the clearest picture yet of quark-gluon plasma, showing for the first time in a smaller collision system the extreme state that defined the early universe. LHCb focuses on a single question: why does matter exist? The universe should have produced equal amounts of matter and antimatter in the Big Bang. They should have annihilated each other completely. Something tipped the balance. LHCb searches for that asymmetry by studying particles called B-mesons, which contain bottom quarks, and comparing how matter and antimatter versions behave differently. Each detector generates data continuously. The LHC produces around 1 billion collisions per second. CERN's computing systems filter that torrent in real time, keeping only the events that look interesting, discarding the rest, and still store over 30 petabytes of data per year. Number 8. The scale of what's being asked. The deepest question a machine has ever been built to answer. Step back for a moment and look at what this actually is. A 27-kilometer ring, 100 meters underground, cooled to temperatures colder than deep space, carrying 2 beams of protons moving at 99.999991% the speed of light, crashing them together 1 billion times per second, with detectors the size of cathedrals analyzing the wreckage, and a global computing network processing the data. The purpose of all of this is not to make something, it's to look at something. To look at what matter actually is, to answer questions that have existed since humans first looked at the world and asked what it's made of. The standard model of particle physics, the current best description of what everything in the universe is made from, describes 17 fundamental particles. The LHC confirmed the last missing one in 2012, but the standard model is known to be incomplete. It doesn't explain dark matter. It doesn't explain why gravity is so much weaker than the other forces. It doesn't explain why there is more matter than antimatter in the universe. The LHC is looking for whatever comes next, for particles that live outside the standard model, for cracks in our description of reality. Right now, in 2026, the LHC is in its final year of Run 3. Within the next few years, it will be upgraded into the high-luminosity LHC, a version that will produce 10 times more collisions per second than the current machine, running until the early 2040s. The most powerful machine ever built by human civilization is a question with a tunnel attached to it. And the question is this: what is the universe actually made of? We still don't fully know. 8 stages. Hydrogen stripped to protons in a bottle. Linac 4 accelerating ions through a stripping foil into bare protons. The booster, the PS, and the SPS handing the beam through 3 generations of accelerators. A 27-kilometer ring cooled below the temperature of outer space, held by 9,300 superconducting magnets. Radio frequency cavities nudging protons to 6.8 trillion electron volts over 20 minutes of lapse. The collision, energy becoming matter 1 billion times per second. Cathedral-scale detectors reconstructing particles that die in billionths of a billionth of a second. And at the center of it all, a civilization asking what reality is made of and building the largest machine in history to find out. 1 bottle of hydrogen gas, 13.6 trillion electron volts, the most powerful particle collider ever built. And we're still not done with the question. Subscribe to Cosmic Hives. See you in the next one.